Let's do some chemical naming. So let's say if we have the compound NaCl. Now, Na is an element. This is something known as sodium. And you have Cl right over here. This is something known as chlorine. Now, the thing is, you can tell that these are two different elements because, well, you can kind of see how like an element starts out with a capital letter. So notice how this Na right over here, right? This represents one element, and you have a capital letter signifying that this is another element right over here. All right, so how do we name this? First of all, after identifying what elements you're dealing with, you have to ask yourself, is this an ionic or is this a covalent compound? Is this a covalent compound? Ionic compounds are created between metals and nonmetals, while covalent compounds are just nonmetals. Sometimes it can be semi-metals, but we're going to get into that later, so don't worry. Or just for now, just know that covalent compound is only made up of nonmetals. Ionic compound, there's a metal and there's a nonmetal. Now, the thing is that Na is a metal. Or if you look on your periodic table, I actually labeled it here, but all the things I surrounded in green are your metals. Group 1 is basically, I like to think about groups as basically columns in the periodic table. So the first column of the periodic table, or the first group of the periodic table, you have your alkaline metals. Group 2 is your alkaline earth metals. And basically, this big thing right over here, these are called your transition metals. So this sort of big block from group 3 to 12, those are going to be your transition metals. Now you're going to have a little bit of a staircase here. So you're going to have a little bit of a staircase sort of thing. And all of this, so all of the things I highlighted in blue, so all of these elements right over here, these are your semi-metals. Basically sort of like a half metal, right? It exhibits properties of a non-metal and a metal at the same time. And finally, the things in red, those are your non-metals. Now, this element right over here, feel free to comment what you think in the comment. This is something known as astatine, but some people say that this is a metalloid. Some people say that this is a non-metal. So feel free to comment what you think about this element. All right, let's get to work. So Na, metal, Cl, non-metal. Metal plus non-metal, that's an ionic compound. And when you're dealing with ionic compounds, what you're going to do is you're going to keep the first thing the same. All right, so you're going to continue with sodium. However, you're going to add an IDE basically for the ending of the second element. So for the first element, you keep it the same. But for the second element, you have to change the ending of it. So in fact, chlorine right over here is actually going to become chloride, right? So you add an IDE at the ending. And yeah, that's how you name it, sodium chloride. Let's do another example. So let's say if we have this right over here. Now, all right, so I'm just going to give a couple more examples. So let's say KBr. So name this ionic compound right over here. K is this, Br is this. K is potassium, B is bromine. So remember that this is bromine right over here, and this is the K represents potassium. Remember what you do to ionic compounds. You keep the first thing the same. So the first element, right, we said that was potassium. But remember, your ending for the second thing, right, the second element right over here, the ending for it has to end in IDE. So bromine becomes bromide, right? So this is going to be potassium bromide, and that's going to be the answer, right? It's sodium instead of chlorine, chloride, right? Bromine becomes bromide. We can do another example. So let's say if we have CaI2 and this. All right, so name this. Well, Ca is a metal, and this is calcium. Iodine, basically this I right over here, that's a non-metal, right? So metal plus non-metal, right? But remember that the ending has to end in IDE, right? Remember, you have to end this thing in IDE. So iodine becomes iodide, and that's going to be our answer. So yeah, keep the first thing the same, just add IDE at the end, and then that's going to be your answer. Now, remember back to ionic compounds. So if we dig a little deeper into ionic compounds, what's happening, right? So let's say if we have Na and we have Cl. Now, Na has something known as one valence electron. Basically, the valence electron, that basically just represents an electron on the outermost shell of an atom. So let's say if I were to draw an atom of sodium. So a sodium atom would look something like this. So in the middle, this is your nucleus. And remember that in a neutral atom of Na, well, an atom of Na has 11 protons, right? Because, right, look at the element, right? The numbers right over here, the bolded numbers basically represent the amount of protons that each element has, right? Because each element is defined by having a different amount of protons than another element. So hydrogen atoms, they only have 1 proton. Lithium atoms, they only have 3 protons, right? An element is defined by how many protons it has. So in a neutral atom of sodium, if we're just talking about a neutral atom of sodium, right? Well, it's going to have 11 protons, and it's going to have 11 electrons. Protons have like a positive charge, right? Electrons have a negative charge. So the charges balance out, and that's what makes it neutral. Now, if I were to draw an atom of sodium, it would look something like this. Right. Okay, so you're going to have 2 electrons in the first shell, 8 electrons in the second shell. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1 electron in the outermost shell. Notice how you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. All right, so we have 11 electrons. And I know I'm like talking about like a lot of topics at once, but also remember that the first shell of an atom, right? The first shell of an atom can only hold 2 electrons. The second shell of the atom can hold 8 electrons. And the amount of electrons that a shell can hold follows the formula 2n to the second power. So in this case, if n is equal to 1, aka my first shell, right? Because we're on our first shell, n is equal to 1 represents my first shell. Well, then when I plug 1 into n, I get 1 to the second power, which is 1. 2 times 1 is 2, right? So it can only hold 2 electrons. If I plug in n is equal to 2, aka my second shell, into this formula, I get 2 times 2 to the second power. 2 to the second power is 4. 2 times 4 is 8. And you can do this with as high shells as you want. If you want to find the amount of electrons you can hold in the fourth shell, well, then you just plug it in the formula. 2 times 4 to the second power. That's going to be equal to 32, right? So that's kind of how you do it. Anyways, atoms, sometimes they want to give away electrons. And the reason why is because they want 8 valence electrons in the outermost shell. So valence electrons are in the outermost shell, but atoms want 8 valence electrons, all right? And notice how for sodium, for an atom of sodium, it only has 1 valence electron, right? It has 1 valence electron in the outermost shell, and it wants to give it away, all right? Because if you get rid of this electron right over here, notice how you're just left with 8 valence electrons, right? In the outermost shell. So if you get rid of this 1 electron, well, then you're going to have 8 valence electrons, and the atom is going to be stable. Now, if you're taking a look at Cl right over here, Cl has 17 electrons. So if I were to draw Cl, it's going to look something like this. So I have the nucleus in the middle, and it's going to be 1, 2, 3. So 2 electrons in the first shell, 8 electrons in the second shell, 3, 4, 5, 6, 7, 8. So we have, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 electrons in total, and it has 17 electrons. So there's going to be 7 electrons in the third shell. All right. 6, 7, 1, 2, 3, 4, 5, 6, 7. All right. Notice how Na has 1 valence electron, and chlorine has 7 valence electrons. So chlorine wants to gain an electron, okay? The reason why is because, think about it, right? It would be much easier to just gain 1 electron and have 8 valence electrons in its outermost shell, right? Remember, atoms want 8 valence electrons in the outermost shell. It would be very easy to gain 1 electron than just to throw away 7 electrons, right? That would be a little too hard for chlorine. So if I only gain 1 electron, then I have a full valence shell. And meanwhile, chlorine is saying, okay, it's too hard for me to gain 7 electrons. I want to throw away this 1 electron. So you kind of notice that, well, these two atoms, what they can do is sodium can give away this 1 electron that it does not need, and chlorine can accept this. So now notice how you notice how once the electron is gone, sodium has 8 valence electrons. And now chlorine also has 8 valence electrons. So both atoms are happy. All right, so now instead of 7 valence electrons, you have 8 valence electrons. All right. Now the thing is that once a sodium atom loses electrons, well, it's no longer a sodium atom anymore. All right. A neutral sodium atom, right? This is a neutral sodium atom. This is something known as an ion. All right, so when a sodium atom gives away an electron, well, it just lost a negative charge, right? Remember, originally, sodium started out with 11 electrons and 11 protons. But now that it has given away an electron, now it only has 10 electrons. And now I don't know why I'm drawing 11 there. Notice how after this exchange, sodium only has 10 electrons and it still has 11 protons, right? You have the same amount of protons as you had before, you just lost 1 electron. So now notice how you're more positive than you are negative. And in fact, you're positive by 1 amount, right? You have a net positive charge in the sodium atom. So when an atom gains a charge, it becomes an ion, okay? Now, if sodium lost, for example, 2 electrons, well, this would be an Na2 plus ion, right? Originally, if it gave away 1 electron, well, there's only going to be a net charge of +1, right? Because you have 1 more proton, 1 more positive than negative, right? So it's going to be a +1, Na+1 ion, right? But if you lost 2 electrons, if Na, let's say, had 9 electrons, well, there would be an Na2 plus ion because now you have 2 more positive charges than you have negative charges. Anyways, so we know that Na becomes more positive, right? So if we are, all right, so I'm just going to put all this in brackets, and I'm just going to put a positive sign here to indicate that this has like a positive charge. Okay, let's say if we're talking about the chlorine atom. Originally, the chlorine atom started with 17 electrons and 17 protons. But now it has gained an electron, and it has 18 electrons and 17 protons. So notice how it has 1 more negative than there is positive. Hence why this is a chlorine anion. This is a chlorine ion. All right, so this is a chlorine, or actually a chloride ion. All right, chloride ion, because you have gained 1 electron. So all of this right over here becomes negatively charged. Now, what do opposite charges do? They attract each other, right? So it's not really the fact that, you've given 1 electron, right, to another atom, and, now these 2 atoms are happy. But it's not that the atoms are happy that attracts them together, right? It's not the fact that the atoms are happy that makes this an ionic bond. It's actually the opposite charges that come from the electron exchange that make it so that they attract each other, right? Because a positive gets attracted to a negative, right? Think about 2 sides of a magnet, right? 2 opposite sides of a magnet attract each other. And this is the same case here. So when you're dealing with ionic compounds, you're essentially dealing with 2 ions, okay? Essentially dealing with kind of 2 ions. The positively charged ion is called a cation, while a negatively charged ion is called an anion. So ionic bond is basically a cation getting attracted to an anion. Okay? All right. I went on like a big rant there. All right. Let's do magnesium. All right. I accidentally said it. All right. Let's just do this compound. All right. How do we name this? So this right over here is something known as magnesium. And this right over here, this NO3, this is something known as nitrate. All right, this is something known as nitrate. Nitrate is something known as a polyatomic ion. The reason why it's called a polyatomic ion because it's an ion that's made out of pretty much more than one atom. So nitrate is actually NO3. Sorry, I didn't put this here earlier. NO3 minus. All right, so it's like this group of atoms, right? It's a group of atoms that have a specific charge. All right. Now, naming for polyatomic ions is easy because you literally don't change the polyatomic ion name, right? Because the first example we saw, sodium chloride, right? You change, basically, you turn chlorine into chloride, right? Change the ending. But for magnesium and this nitrate right over here, you actually, right? Remember, you keep the first thing the same, but for a polyatomic ion, you actually don't change the name of it. So this is just called magnesium nitrate. Yeah, you just don't change the name of it. We can do more examples. Let's say if we have CaCO3. This right over here is calcium. This right over here is carbonate. So the name of this is calcium carbonate. Let's say if we do this. Let's do this. All right. So this right over here is ammonium. This right over here is ammonium. And this right over here is chlorine. All right. Now be careful. Remember that for the first thing right over here, right, because our first thing is a polyatomic ion, it stays ammonium, right? Remember the first atom, always the name is like the same as it is before, right? But for the second atom, you have to change it so this becomes chloride. So in this case, this is ammonium chloride, right? You might be confused, but the thing is, like, remember that calcium carbonate in this example. Remember, notice how like CO3. Notice how CO3 is basically our second sort of thing, right? It's our second thing in our compound, right? The first thing right over here is our metal, and then the second thing right over here, this carbonate right over here, is basically you can think about it as our anion, or a lot of times it's non-metal. You usually have to change the non-metal's name. But for if a polyatomic is an anion and it's at the end, you don't change it. Or if it's at the front, right? If it's at the front or the back, you do not change the name of it. It's only just single elements, all right? Single elements at the back, that's the only time you change the name of it, all right? So if you have just a single element in the back, right? Single element in the back, that's going to be when you change it. So in this case, ammonium, and then this is going to be chloride. You don't change the polyatomic. You never change the polyatomic. You only change things in the back that are elements. I'll just do another example because that might seem a little bit confusing. So if you have, let's say, K2SO4. All right. The way you name this is this right over here is potassium. And this is sulfate. So this compound is called potassium sulfate because, remember, you do not change the name of your metal, aka the cation, right? You don't change the name of this, and you also don't change the name of the polyatomic, even if it's in the back. All right. I'll do another example. If we have something like NH4, once again, NH4, and let's say F, right? This is right over here is ammonium. And this right over here is fluorine. Oh my God, my spelling. Right, but you have ammonium in the front, and it's a polyatomic, right? So you don't change the name of it. And the element right in the back, we just have a single element. If the thing in the back is a polyatomic, we don't change it. But if the thing in the back is an element, then remember fluorine, you got to get that IDE ending, fluoride. That's going to be our answer, ammonium fluoride. Okay. Now let's see. Write the formula for calcium phosphide. So how do you write the formula? Now we know how to name the compound, but how do we actually write out the compound for an ionic compound? Now calcium right over here. Notice how calcium is on group 2 of the periodic table. That means that calcium likes to give away 2 electrons. All right, I'll say that again. All right, things in the same group. All right, so I'm just saying really quickly, but things in the same group have the same number of valence electrons. So in this case, group 2 has 2 valence electrons, all right? It has 2 electrons in the outermost shell. Now, it has 2 electrons in the outermost shell, and it's a metal. And remember that metals, right? We saw with NaCl, other examples. But we saw that with metals like to give away electrons, right? That's why metals become cations, which are positive, right? Because you're giving away the negative charges. So if calcium has 2 electrons, it's gonna, in the valence shell, it wants to give away those 2 electrons in order to have a full valence shell. So it's gonna form a calcium 2 plus ion, right? That's why for all the group 2 elements, notice how it likes to form a +2 ion, right? It likes to give away 2 electrons because it has 2 valence electrons. Well, phosphide, that's going to be a -3 charge, right? Because phosphorus is in group 15, right over here. Now, group 15, I like to think about it like this, all right? So instead of phosphorus being in group 15, I like to kind of rename my groups. So this is group 1, this is group 2, and you have group 3A, group 4A, group 5A, group 6A, 7A, and then 8A. Okay, so you kind of just skip over the transition metals and you kind of name it normally. All right, so you increase by 1 every time. Group 3A, all the atoms right over here, pretty much all the atoms right over here, want to give away 3 electrons, right? That's why it's group 3A. Then you have group 4A. These atoms either like to lose 4 electrons or it likes to gain 4 electrons. It's like a sort of like a 50-50. I mean, because think about it, if you have 4 valence electrons and you're trying to get 8 valence electrons, it's kind of like some atoms, they might like to give away 4 electrons. Some atoms, they might like to gain 4 electrons. So it kind of depends on the scenario. And this is kind of when you starting from pretty much group 5A to group 8A. This is pretty much when the atoms start to kind of gain electrons. This is kind of the turning point where atoms like to start gaining electrons instead of losing electrons. So from group 5A, all these elements right over here have 5 valence electrons, right? Hence why it's called group 5A. So if I want to get to 8 valence electrons, how many electrons do I have to gain? 3 electrons. And if I gain 3 negative charges, I'm going to form a -3 ion. If I were to take a look at group 6A, right, I have 6 valence electrons. So if I want to get to 8 valence electrons, I got to gain 2 electrons. If I gain 2 negative charges, I have a -2 charge overall. I'm a -2 anion, and so on, right? So you kind of see the trend. So phosphorus right over here, it has 5 valence electrons, meaning that phosphorus likes to form, where was my example? All right. Phosphorus likes to form -3 ions. All right, because phosphorus has 5 valence electrons. So that means that it wants to give away, phosphorus has 5 valence electrons, meaning that in order to get 8 valence electrons, it wants to gain 3 electrons. So aka it wants to gain 3 negative charges, right? So in order for things to work out, the calcium has to have a 2+ charge, and the phosphorus has to have a -3 charge. Now, you do a special trick called crisscross. So pretty much the numbers become sort of the subscript for the atoms. So in this case, right, this 3 right over here is going to become the amount of calcium that I have. And this 2 right over here is going to become the amount of phosphorus that I have. All right. So I'm going to do that again. This -3 over there, if we do a crisscross, this 3 becomes the amount of calcium that I have, right? The charge, basically the positive number in the charge, right? That's going to become the amount that I have of the metal, right? If I crisscross it like this. If I crisscross calcium like this, I'm going to get 2 here. If I crisscross it like this, it's going to go to the subscript for my nonmetal. So yeah, this is how you write the formula for calcium phosphide. Right, let me just kind of do another example to kind of demonstrate this. So let's say if we have calcium bromide. Calcium, it wants to form a +2 charge. And bromine is in group 7A, aka it has 7 valence electrons. So in order to get 8 valence electrons, how can I make 7 into 8? I have to add 1 electron, right? In order for me to get from 7 valence electrons to 8 valence electrons, I have to add 1 valence electron. Hence why bromine likes to have a -1 charge, right? Bromine wants to form a -1 charge, right? It wants to gain an electron. So now you're going to do crisscross, right? So you're kind of you're gonna rewrite everything, right? So the metal, remember the metal is the thing that goes in the front, aka the cation, and the anion, remember that goes in the end. Now this 2 right over here, that's gonna become the subscript for the bromine. Well, this 1 right over here, you're gonna ignore the charge, you're gonna ignore this negative, right? You're gonna look at this 1 right over here, and that's gonna become the subscript for calcium. So this is going to be calcium bromide. There's going to be 2 bromine atoms for 1 calcium atom. All right, this is going to be the answer. You don't need to write the 1. If you do not write the 1, you're kind of implying that there's a 1 right over here. So you don't need to write that, but just for the sake of this example, I wrote this 1. So you can just kind of see the crisscross. All right. Now, why does this sort of work? I mean, well, the thing is that like ionic compounds, right? They need to be in like the simplest sort of whole number ratio. So for example, if I were to say calcium bromide, so let's say if I were to say the formula for calcium bromide is, let's say, Ca2Br4, notice how this can be simplified, right? Because there's a 2 here and there's a 4 here. And for ionic compounds, you want it to be in the simplest whole number ratios, right? So because you can simplify 2 and 4, they have a common factor of 2, right? So because this can be simplified into this isn't actually the way you write it. And the crisscross method is very good because it kind of guarantees that you're getting the correct ratios, right? I mean, if you kind of look at this, right, calcium, it wants to form a 2+ charge, right? It has 2 valence electrons. Bromine, it has a -1 charge because it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, right? So it wants to gain an electron. Now notice how calcium, if the formula for calcium bromide were just CaBr, notice what happens. Calcium can only give out 1 of its valence electrons to bromine, and there would still be 1 electron left. So calcium wouldn't be satisfied. So this is why CaBr isn't the formula. And instead, you actually need 2 bromine atoms, because guess what? So you have 1, 2, 3, 4, 5, 6, and then 7. So now that you have 2 bromines, each bromine can accept 1 electron. So now calcium is left with 8 valence electrons, right? Because these 2 electrons go bye-bye, so no electrons there. And now each bromine atom has 8 valence electrons, so everyone's happy. All right, you see, the ratio of the cation to the anion is very important, because a lot of times you have to find the correct ratio so that there's no sort of excess of electrons left, right? Everybody's happy. All right. Okay, so now we are going to get into naming covalent compounds. And I'm doing this, I don't know where that went. Okay. I'm just going to do this. And we should be good. All right, the good thing about covalent compounds is that they are actually not that bad to name. I'm not gonna lie. They are not that bad to name. Okay, so covalent compounds, remember that you can tell a compound is covalent if it's just made out of non-metals. So it's sort of like, it's like naming sort of ionic compounds. All right, so the way that you would name, let's say, this right over here. So notice how there's 2 nitrogens and 3 oxygens. All right, this is nitrogen. This is oxygen. Now, if I wanted to name this, well, first of all, I'm just going to put nitrogen. I'm just going to put nitrogen here. The first thing always stays the same. It's sort of like an ionic compound, right? Ionic compound. The first thing stays the same, and the last thing gets the suffix IDE. So it's the same thing that you've dealt with before, right? Oxygen, that's going to become oxide, right? It's going to end in IDE. Now, the thing that changes, though, is that for ionic compounds, notice how we did not actually care about the ratios of the atom. So let's say if I were to look at this right over here. This is we did this example before, but this is calcium phosphide, right? And notice how calcium phosphide phosphide. Notice how we did not take into account the number of atoms of each element, right? For ionic compounds, we don't care about how much of calcium we have or how much of phosphorus we have, right? We only care about what elements are in there. So we only care about the calcium part and the phosphorus part, not the numbers associated with it. But if you were to name covalent compounds, that's when you start caring about these numbers right over here. All right, because there's 2 nitrogens for this covalent compound, you're going to put a di in front of nitrogen. And because there's 3 oxygens in the oxygen, right? There's 3 oxygens here. We're going to put a tri after oxygen, after oxide, sorry. So this compound is named dinitrogen trioxide. This di comes from the fact that there's 2 nitrogens. This tri comes from the fact that there's 3 oxygens. All right, so 2 nitrogen, 3 oxygen. Yep. So yeah, when you're kind of naming these things, remember that remember this chart right over here, and you can easily remember it just by thinking about like simple stuff. For example, if you have 5 of a specific atom in a covalent compound, you have to put a penta before it, right? You have to put a penta before the name of it. What also starts with penta? Pentagon. A pentagon, how many sides does a pentagon have? 5 sides. Hexagon, 6. Heptagon, 7. Octagon, right? So you kind of see like the pattern here, right? Di, you have tri, right? You think about triangle, right? You know what I'm saying? So yeah, there are some really pretty clear trends in the name of this so that, it's easier to memorize. Let's do this. So right over here, we have sulfur, and we have fluorine. Now remember, the last thing always gets a IDE. So fluorine becomes fluoride. Fluoride, right? Fluorine becomes fluoride. Now, oh shoot. The hell? Now, because there's 6 fluorine atoms, we're going to put a hexa, right? We're going to put a hexa in front of fluorine because 6 corresponds with hexa. Now, for sulfur, there's only 1 sulfur. So, are we going to put mono? This is the exception you have to know, all right? Basically, everything else works except for this. When you have 1 atom, right? So notice how sulfur is the first atom on my covalent compound. And there's only 1 of sulfur. So sulfur is the first, and there's only 1 of it. That's when you actually don't put mono in front. All right? You don't put mono sulfur hexafluoride. You only put sulfur hexafluoride. All right? So if there's only 1 of your atom in the front, and it's the first atom, you actually don't put mono at the front. All right? Maybe this example will help clear it up. CO. All right? How do you name this? Well, notice how there's 1 carbon and there's 1 oxygen here. So we have carbon and we have oxygen. But remember, the second atom, oxygen, turns into oxide. Oxide. Now there's only 1 of oxygen, and it's in the second atom. So we put a mono. We put a mono in the front. In this case, we can just put a mon because oxygen starts with O, so it already makes mono, right? So we actually don't have to put a mono oxide, right? We just put a mon oxide. And notice how there's only 1 carbon. But the thing is that carbon is the first thing, and there's only 1 of it. So we actually don't put a mono at the front, right? This is why CO is actually called carbon monoxide. You probably heard of carbon monoxide before. There's a reason why it's not called monocarbon monoxide, right? Because there's only 1 carbon at the front, we ignore the mono. All right? If there's 1 thing in the back, that's when you put the mono. But if there's 1 thing in the front, you don't put mono, okay? So, yeah. So use this carbon monoxide example if you're like stumped about this rule. The same case for here, right? This is phosphorus. And remember that this is chlorine, but chlorine turns into chloride. IDE, right? And because there's 5 chlorines, this is pentachloride. Because 5. Let's do another example. This is 2 chlorines, so it's dichlorine. Dichlorine. And then you have 7 oxygen atoms, so that's hepta, and then oxide. Okay? Do one more example. This right over here is silicon. Silicon is a non-metal. Silicon is a semi-metal. And semi-metals can be in covalent compounds. They can also be in ionic compounds. So this right over here is silicon. In this case, this is a covalent compound. Typically, when you have a semi-metal, I'm just going to put a semi, and it's bonded to a non-metal, it's going to be covalent. But if it's bonded to a metal, then it's going to be ionic. That's usually the case. All right, so silicon right over here, and you have two oxygens, so it's going to be dioxide, right? Di coming from the two, oxide because IDE ending. Sodium arsenide. So this is kind of an example of a compound where you have a semi-metal, right? Arsenic is a semi-metal, right? But because it's bonded to a metal, which is sodium, Na, and then arsenic is, if you look at the periodic table, arsenic is As. Sorry, not As. Arsenic is As. Sorry guys, I kind of just took like an exam today, so like it's a little bit cooked. All right, so but arsenic is As. Sodium is Na. You have a semi-metal bonded to a metal. That's going to be ionic. Let's do a little bit of review for ionic compounds and how to write them out, because you guys are probably sleeping by now. So I want to make sure that you actually gain something. Arsenic, remember, it's in group 5. Elements in group 5, what do they want to do? They want to get 8 valence electrons. How do you get 8 valence electrons? How do you get from 5 to 8? You got to gain 3. So you got to gain 3 negative charges. So arsenic got to gain 3 negative charges. While sodium, it's in group 1. If you have 1 valence electron, it's going to be very easy to just lose it rather than gaining 7, right? Gaining 7 valence electrons, that's a little too hard. Let me just lose that 1 valence electron, right? So sodium wants to lose an electron. It wants to get positive. All right. Now you got to do the crisscross. Remember, the Na and the As stay the same. All right. Na is going to be in the front because it's a metal, and the non-metal, or in this case, the metalloid, is going to be in the back. All right. Metals are always in the front. Now, or you can think about it as cations in the front, anions in the back. All right. So this 3 right over here becomes the substrate for this, and then this is going to become here, and that's the answer. All right. Now, finally, we have remember when you're writing your ions, place the number first. For some reason, I low-key kind of forgot, but I placed the charge first in some of my examples, like this. I placed the charge first for some reason. I'm sorry, guys. It's cook day.